Hello, physics research. This is my second paper. Came out of my research in Government College Lahore during my master in physics. And the title of this paper is a low temperature anomaly in the strength of copper manganese alloys single crystals. And it was published in Physics State Solution A 1990, 2 years after I left Government College Lahore. So the aim of this research is the cause of the low temperature anomaly observed below 75 Kelvin in uh, critical resolved stress versus T temperature data of copper manganese alloy Fig 1 of my previous work, which was published in 1889. So this was the figure which was that show that the uh, critical resolved shear stress. Stress is on the y-axis and the temperature on a Kelvin in x-axis. So these are the dots are the experimental points, and it is continuous line is the theoretical model, King pair model. So and then the experimental curve uh, is goes like this one, bend toward the uh, axis, toward x parallel to x-axis. So these are the two features. If we explain this one, so there are two features come out of this curve. One feature is this one, which is explained on the experimental and theoretical point of view. It's the same, but then is that another trend, which is like this one, which is unexplainable from the theory. So feature one and feature two. So, introduction of this paper is the temperature dependence of critical results shear stress, which I have explained in my previous discussion, CRSS, which is represented by tau in measured in megapascal of copper single crystal from zero point 0.11 to 0.76 atomic percent of manganese. Anomalous behavior of tau T region below 75 Kelvin have been observed, and this shows some short range order of the concentration above above 1 atom percent. So this is the intro, and the king pair model have been used in this study. So king pair formation model of solid solution hardening, where the tau, which is the critical resolve shear stress, is equal to tau naught exponential of minus mkt over w naught. M is the mass, k is the Boltzmann constant, T is temperature in Kelvin, and w is the work function, which is the binding energy of the dislocation. Anomalous mechanism. Anomalous mechanism response of the metal at low temperature is an obstacle to the dislocation. We are using the metal model into the alloys. So this we have observed, which I have discussed in my first paper of 889. So this is the stress, and this is the temperature, and these the dots are the experimental points, and the line is a theoretical model. And this model doesn't look good at the low temperature below 75 Kelvin. So all line bend to parallel to the x-axis. So there are two features. One is where the theory and the experimental matches, and another one which there has no agreement. So feature one and feature two. So anomalous behavior of copper manganese alloy for different concentration of C1 and C2. This is explained. So the deviation from king pair model described as this expression, king pair model, as a solute concentration depend upon the temperature, but we have here is independent, but but it has been established that the solute concentration is depend upon the temperature T. So this is two figures describing V naught and L naught. V naught is the activation volume, and L naught is the initial length of a dislocation segment, which breaks away from the solute atoms under the action of stress T naught, and then undergo maximum distance and be in activation process. So this is volume and this is the length, and they are both concentration dependent, and if the value have about 1, this is 1 10 to the power 0 1 atomic percent, this is also 1 atomic percent, and this problem here is also at the same concentration. So there are two features, and two parameters have the same variation changes. So therefore, a stress concentration factor F is defined. This is F T, which is equal to T imperial empirical plus T naught over T empirical plus T. Ft is equal to 1 when T is equal to temperature is equal to T naught initially, and then Ft is greater than 1 when T temperature is less than T naught. Okay, so for this one, so Ft is equal to 1, and where temperature is equal to T0, and Ft is greater than 1 when temperature is less than T naught. So this range is this function varies. This function varies between 1 to 2.7, and this, when C the concentration is dilute, 0.03 to between 1 um, atomic percentage. So this is the function. So this function is as the concentration varies. This one, so it goes maximum, and then this one. So this maximum is also the same as the other graph. So this graph where here is the have this one. So if this has a one profile, and then it jumps again, and then it has this one. So this is a feature 1, and this is feature 2, which I have explained to you. That this one, there's two curves. So this one, feature 1 and feature 2. So T empirical is a constant, and T naught is a critical temperature. So when C is below and the T is tau 0 is 6.4, and T is 75 Kelvin, and T empirical is 180 Kelvin. So similarly, another one is zero point 0.2, and then there's a variation of this one. So now the temperature stress of function of T, which we have used in the formula of tau is equal to tau naught exponential minus mkt over w naught. So this will be changed to this function of ft. So empirical constant versus concentration is given this one, so that will fit this one. So anomalous mechanical response of copper manganese at a low temperature is influenced by T empirical over C curve, this one, rather than just as a C curve, which is this one and this one. Uh, then the relationship tau T is equal to this one with a correction factor Ft holds good. So this is the correction factor. We have to assume this one. So to fit the boundary conditions so that there are the two uh, kind of features, uh, low concentration and high concentration, to explain the anomalous behavior. So that's it. So that is we have explained beautifully by using the boundary conditions and the two conditions and two limits and one correction factor in the original king pair model.